Hi, Adam Baker from Affinity Energy. Today I wanted to talk about some of the decisions that get made in the process of designing how a control system for a solar power plant is going to work. Some of these decisions are probably things that most customers don't really think about, but they come up from time to time depending on whose application, whose interconnection agreement, where the site is located, and some of the things that are kind of forward-looking that'll allow us to embrace the technology that we know is coming and be ready for it rather than trying to retrofit it into a control system that was designed without the capabilities to use battery storage as an example. So I have the analogy of a tree and the decision tree that gets made in designing the control system for what components are going to run where within the control system, how they're going to work. And I just wanted to walk you through the decision tree that I go through in figuring out how a control system should work for a particular site. And it's we're going to use the analogy of the leaves on the tree. So if you're not familiar with Affinity Energy, we are a control systems integrator. We've been in business since 2002, started with a focus on general controls, but have over the course of the last 8 years really had a high degree of focus on critical infrastructure and power applications. The business unit that I work with is focused highly on PV solar. So I've been in the business since 2009 doing solar and have worked on sites anywhere from a megawatt or below all the way up to 550 megawatt sites out in California. So I've seen quite a variety of different needs in the industry, and I've seen the industry grow quite a bit since 2009. So within controls and PV solar, there are two kinds of powers you're probably aware. There's active power and there's reactive power. And how we do control of the two things are almost completely independent of each other, though there are some interdependencies. But for the first, the money part of the equation, active power control modes, there are several things that we need to think about when we're doing controls. So these brown leaves represent legal documents that need to occur in order for there to be a solar project. There's a power purchase agreement, and that really comes down to what are you going to get paid per kilowatt hour for the energy that comes from the site. And there's an interconnection agreement, and that defines what the rules are for how much power you can deliver, what the voltage is going to be, what the voltage conditions the site should be able to tolerate are, and other parameters around which the site should operate. So the second agreement talks about how things have to happen, and the first agreement talks about what things you're going to get paid for. There's also a third agreement that I don't list here. It's basically a conditional use permit, so that's your ability to use a patch of dirt for a period of time in order to put the solar power on. With a power purchase agreement and an interconnection agreement, you've got a plant megawatt set point. So the interconnection agreement will define what the maximum amount of power that you can put out of the plant is. The interconnection agreement will often define how many inverters and how many megawatts of inverters are allowed on the site. You would think that once you know how many megawatts you want to make, how many inverters there might be, that all we can do is now just do the division and you have a megawatt per inverter command. But in my experience, how things are calculated, how the control system functions is a lot more complicated than that. So here's sort of a walk through some of the other ideas. So the red leaves represent the things that need to be considered in every solar project when you're doing a control system. Is the plant capacity the same as the maximum active power output of all the inverters aggregate? So if you have a 100 megawatt site, and you have 100 1 megawatt inverters, then you can't exceed 100 megawatts. But earlier in my career, a lot of the sites that we built, almost all the sites we built, had more AC capacity than the interconnection allowed for export of power from the site. So we'd have a 100 megawatt site, but 120 megawatts of inverters. And that allowed us to compensate for things like when a cloud came over the site, we could turn up the output to compensate for the cloud going by. But it also meant that we needed to curtail the inverter output all the time unless the conditions, the environmental conditions were such that you couldn't get to the interconnection agreement. So if your plant capacity is equal to what your inverters can produce, you have a relatively, at least on the start, a relatively simple control system. You only have to concern yourself with curtailment. Often in the interconnection agreement, there are stipulations of what the rules for ramp rate are. Most commonly in the industry, 10% per minute of plant nameplate capacity is the norm. So if you've got a 100 megawatt site, you're going to ramp at 10 megawatts per minute. For active power, and that's going up as well as going down when you're doing a controlled shutdown of the plant. In the case where a cloud comes or there's some impeded irradiance, you can't control how fast the site might ramp down, but you should always ramp the site up and down in an organized, orderly fashion whenever you can, whenever it's possible to do that. So what are the ramp rate parameters? Are they spelled out in the interconnection agreement, or do you want some ability to ramp faster? The third topic here is frequency droop. And frequency droop is something that is oftentimes handled by the inverters. The IEEE rules require that the inverters respond to changing frequency conditions by turning down output in an over frequency condition. There may be a good reason why you would want to have frequency droop handled by the plant control system. That's particularly the case if you have an overcapacity on AC and want to turn up the total output of the plant, or if there are different sources of energy. Maybe you've also got some battery storage on the site and you want to use battery storage to respond to an under frequency condition by turning up output. So the central control system may be the device that manages frequency droop in the case of over or under frequency, or you can let the inverters do it, but you better choose wisely which of those paths you want to go down. It's really hard to change once you've chosen a path. So are we ready to send an inverter command yet? Not quite. There's a little more to think about. The yellow leaves represent the things that you may have to deal with for a particular project. Things that are often not really considered in the design of the control system, but I believe always should be. So now we have an active power command, but you might have multiple sources of command for active power. It might come from the local HMI screen. Somebody sets you want 100 megawatts of output. It might come from an energy management system where the owner of the site is sending a command that they want the site to run at. Or there might be a feed from the balancing authority that has the ability to turn down or curtail your site automatically. So you have multiple potential sources of your set point for active power, and you'd have to choose by priority which one you want to follow and when. Then we've got closed loop control for active power, so you need a source of feedback in order to do closed loop control. Most of the time, every bit of time when possible, the primary high side meter should be the source of information of what the active power reactive output from the site is. However, in a case where a primary meter might not be available, is there a secondary meter that you can use as a source? Is there a low side meter that you can use with some calculations to figure out what the high side output might be? Or can you aggregate the information that you're getting from all the inverters, add those up for kilowatts and kVARs, and calculate what your output from the site would be if you didn't have any meter feedback? So a decision around what to do if there's a loss in metering telemetry is an important decision in the process. So the third thing on this branch of the tree is the number of inverters that are available and the number of inverters that aren't available. So if an inverter that is designed in your system is not communicating with the control system, you can't control it. So if you're not getting any feedback from the inverter, you probably can't command it to change its output. So now if a few inverters at the site are offline and you're trying to ramp the site up or changing set point, the amount of ramping that you need to do with the other inverters is bigger than what would normally be your 10% per minute ramp rate. If half the inverters at the site aren't running, then you want to ramp the rest of the inverters at 20% per minute, which will give you an overall site ramp rate of 10% per minute, because that 10% per minute is based on the nameplate capacity. So when you have inverters that are unavailable, your ramping parameters and your active power parameters are going to change based on what you can control versus what you can't control. So now, are we ready to issue an inverter command yet? we got another branch or two to talk through. These orange leaves are things that I rarely see people properly handle in a control system, but I definitely recommend considering as you want to have the most robust control system possible. The first topic here is power that comes from an uncontrolled source. So sticking with my example, I've got a 100 megawatt site. I'm communicating with 50 megawatts of inverters, but my meter is telling me that the site is making 70 megawatts of power. So there are now 20 megawatts of inverters that are running, but I can't control. So if I need to do anything to ramp up or ramp down the site, I've got to redo all of my calculations for ramp rate and for what my target set point is, based on the fact that there is an uncontrolled source of power somewhere in the site that's going to contribute, whether I want it or not, at the point of interconnection. And also, I need to pay attention that that uncontrolled source of power is subject to the same variability from clouds and everything that the part that I can control is. So if I've got 20 megawatts now, that doesn't mean I'm not going to have 25 megawatts in 5 minutes or 10 megawatts. So we need to do all of our control based on the actual output of the site, including both that which we can control and components that we might not be able to control at the time. The next fun topic with solar inverters is the requirement that the inverters, from the time they're given a command to start, wait 300 seconds before they actually start. There's a good reason for this time delay. So if there's a distributed generation connected solar site and there are problems on the line, maybe there's a windstorm and there's trees hitting the lines somewhere up or down the line, the stability of the line might be such that you don't want to reconnect the generation if there's a short disturbance. Also might be the case that if there are workers working on the line, the inverter is going to wait for 5 minutes with reliable power before they kick on. And that way, if somebody is working on the line, closes in a breaker, the inverters aren't going to just jump on, start producing, delivering power. But the downside of that is if I command an inverter to start from the control system, depending on the site and how the inverters are configured, I may or may not be able to get power from those inverters in the short term. So I can command an inverter to start, but it may not be able to deliver power for up to 5 minutes. So I've got to keep track of that, because even though it's waiting, it's warming up, it's grid sync mode, not delivering power, when that 5-minute timer expires, that inverter is going to jump to the command that it's being given. So where I see trouble with this most frequently is if somebody's doing maintenance at a big solar site, and maybe a feeder breaker is open. Now there's 20 megawatts of inverters that aren't running. You close the feeder breaker and those inverters are not able to deliver power. And this falls into the category of are they available or are they unavailable that you have to keep track of. And I keep track of a mode that is in transition, meaning they're not yet delivering power, they're going to, and here's the time between now and when they're going to start so that I can preemptively ramp down the site knowing that these additional inverters are going to come on shortly towards the end of that 5-minute delay. One of the last things about inverters is their dynamic response profile. So each flavor of inverter I've ever worked with has a slightly different response when it comes to I issue it a command, how long is there a delay before the inverter starts doing what I've asked it to do, and how fast is it going to get to the commanded output that I've asked for. So it might be a couple hundred milliseconds between when I issue a command to an inverter and the inverter actually responds, but it might be more than that. Some inverters will be quick, some inverters will be a little bit slower. And then if I command an inverter from 0 to 100% output, how long is it going to take to ramp from 0 to 100%? And that's another parameter that's set in the inverter but might vary from site to site. So in my control algorithm, I have to take account for any of the delays in the system between when I issue a command and when the inverter does what it's told. So once we've considered what the status is of all our inverters and whether or not things are running, what the behavior is going to be, got the system tuned for what we've got. Are we ready to send an inverter command? In many cases, yes, but there are a few more things that are a little more forward-looking that we might want to consider as a last thought before we issue a command. So the last green leaves are things that are infrequently found in solar, but are definitely things that should be considered for the future and might be capabilities that you want to integrate in from the beginning, even if they're not something that you have in place right now. So for instance, in island grids, very small grids like Hawaii, Guam, Puerto Rico, very small grid applications, cloud-affected ramp rate limiting is also a factor. So not only do we need to ramp the site output up and down in an orderly fashion, 10% per minute, during normal conditions, but also if a cloud were to come and depart from the site, you need to ramp the site back up from the lowest output due to clouds at that same 10% per minute. And it's not at all straightforward on how to do this. You can turn down the response of the inverters and make sure that you ramp more slowly than 10%, but ultimately that means that you're costing the owner money in underperformance through whatever frequency of clouds are coming to the site. Oftentimes, if there are, especially morning or late in the day, clouds or fog at a site, trackers are going to point towards where they think the sun is. And if you've got a tracker that may point 60 degrees to the east in the morning, if you've got a morning fog or you've got some clouds that are giving you a lot of diffuse irradiance, you might actually be able to deliver more energy by flattening the position of the trackers instead of pointing towards the sun. When there's a lot of diffuse irradiance, horizontal irradiance would be higher than what the plane of array irradiance is of a module that's pointing 60 degrees over towards the east. This control system has access to the data that comes from the MET station, so you can actually know that this is the case. Comparing the GHI irradiance with the POA irradiance, and something needs to be able to tell the trackers that what they think they're supposed to do isn't maybe what's best for the energy output of the site at that point in time, and something needs to be able to override their position. And the last thing that is more frequently thought about today, but is a critical component to the control systems moving forward, if you're going to integrate battery storage, there is the thought process and algorithm about when batteries should be charged and when they should be discharged, whether you're trying to time shift energy, whether you're trying to limit ramp rate going up or going down, or how exactly you're going to use the stored energy of the battery system. So do you want to charge off of solar during the day or do you want to charge at night? These are considerations that also need to be factored in. And there haven't been a lot of battery storage sites, but we know that there are going to be a lot of battery storage in the future. So now, once we've got all of these thoughts in our head and we've made decisions on how we're going to consider all of these things and controls, all of the puts and takes that go into these things give us the ability to determine what the inverter command should be right now for this moment in time in order to optimize the system. Now that we've gotten all of these leaves considered and all of the decisions integrated into our control system, the control system doesn't have to deal with making the decisions over again. The control system just has to recalculate what the inverters should be doing with all these considerations over and over again. So now that we've gone through 5 branches and 14 leaves worth of considerations, we're done talking about active power control. Now we can dive into the more complicated topic of reactive power control. If up till this point you've been doing primarily distributed generation sites, 5 megawatt smaller sites, not tied to transmission, then the reactive power modes will be a new topic to you. But if you've been doing a lot of bigger sites, large LGIA, large generator interconnection agreements, reactive power modes are going to be something that you're familiar with, but there will probably be some topics in here that you haven't considered to date. So the first topic is which mode of automatic voltage regulation, or AVR, you're going to use. Most commonly, a few years ago, sites were in power factor mode, and they were set to unity power factor. So everything that came out of the site was 100% real power, and you didn't really have to deal with voltage. As time has gone on, I'm seeing more and more sites that are required to do voltage control and are running in voltage control full time. So it makes it a little more complicated. But the first thing you need to know is that there are at least 3 different modes: power factor mode, a fixed VAR output from the site, and a voltage control mode. You need to know which modes are required and which modes you're going to operate in. I'd argue that the easiest mode to do is fixed VAR control, where the site is delivering some amount of VARs to the grid all the time. The inverters generally are running in reactive priority mode, so if you command 10 kVARs from each inverter, you're going to have some line losses through the site, but basically you're going to get out from the site the same amount of VARs all the time, regardless of what the variable irradiance is. With power factor mode, which is the second easiest mode, then you're trying to have some proportional amount of VARs for the active power that's being generated. The inverters are generally going to be controlled as a VAR command, but the calculation for how many VARs will be based on what the output active power is from the site, so that you can calculate how many VARs you need for any given amount of active power in order to attain the power factor that you're commanded to. This can also be tricky in the design of the site, in the determination of whether cap banks are needed. When you've got VARs going through a medium voltage transformer and a high voltage transformer, you've got a lot of losses. So will the inverters be able to deliver enough VARs to meet your interconnection requirements or additional static VAR devices required for the site? So those are the relatively easy modes. The last option of voltage control mode actually has sub-options within it, and I'll sort of deep dive on this one leaf. So here we've got a horizontal axis that gives us whatever the grid voltage is from feedback. If you're connected at 115 kV, that 115 kV is a nominal voltage for that transmission line. The site itself at the interconnection is going to have likely a different grid voltage at that point. Usually it's higher, so it might be 117.5 or 118 kV. That's going to be your nominal set point for the site. Then from 118 kV, there may be a defined deadband. So if it's 118 kV plus or minus 2,000 volts, then whatever the automatic voltage output is from the site, leave it alone. But if it goes above 120 or below 116 kV, then we want to either buck grid voltage or boost grid voltage with some VAR support. The VAR support will always come in the form of VARs, but it could be commanded based on one of 3 things. Either PI or PID control, where we're just trying to inject enough VARs to get back to set point, and that proportional integral math over time gives us a nonlinear response to the deviation. Or we can define a couple of linear response modes where if the voltage is high, adjust the site's VAR output to consume so many kVARs per kV above deadband, or add so many kVARs per kV below deadband. And the slope of the rates above and below might be different. Or you can change the site's power factor based on a deviation above or below the deadband. If you're at 122 kV, but you're trying to maintain 118, you may want to change the site's power factor to a negative 0.98 to try and reduce grid voltage. Whatever the slope of that line is above and below, those points need to be defined, and then the width of the deadband above and below the nominal target also needs to be defined. And each of those 4 values can be different. So there are some decisions to be made in how the site should respond to voltage deviations. And that is usually a long, deep technical conversation with the transmission operator. Next, we have the ramp rate, which again, how fast do you want to ramp VARs? As a rule of thumb, if your active power ramp rate is 10% per minute, as is the normal, the ramp rate for VARs that I use most frequently is 10% per second. So it's a much faster ramp rate than active power. You want to respond to the voltage deviations much more quickly, but you don't want instantaneous VARs. The last consideration that comes from the interconnection agreement is what is the required power factor range that the site must be able to operate in. And this lends itself back to the comment I made earlier about whether cap banks or an inductor bank might be required for the site. If the power factor required range, the norm is sort of a plus or minus 0.95, but I've seen other interconnection agreements where they're much broader. It might be a plus or minus 0.9 or even plus or minus a 0.85. And in those cases, you're going to need some source of supplemental VARs beyond what the inverters can produce, or you're going to need to oversize the inverters, or you're going to need to put in more inverters than you really have a need for from an active power requirement standpoint. So do we have enough information yet to send a VAR command to the inverters to reach our AVR set point? Of course, by now you know there's a little more to talk about here. So again, like with active power, there can be multiple sources for what the voltage or AVR set point should be. It might come from HMI, it might come from energy management system, the balancing authority, or we could just have an override algorithm in the control system that says, based on these conditions, here's what we need to do. So a set point can come from multiple locations, and the controls can interpret set point based on line conditions. We have the same considerations with number of inverters that are available. If we have to make so many MVARs for the site, do we have enough inverters available to produce the MVARs out of the site that are required, or do we need to use static VAR compensation? Are the inverters set up for active power or reactive power priority? In my experience, 100% of the time, the inverters are set for reactive power priority. VARs are more important than active power from a grid stability standpoint. Even though you're probably not getting paid for VARs, you are required by the interconnection agreement to be able to support the VAR requirements where the site is running, and that is more important than delivering power. So inverters, reactive power priority is the norm. If you're in a desert location, a high temperature location, will the inverters have a thermal derating that is going to affect their ability to deliver VARs, power factor, or active power? Is there a thermal derating consideration that you have to consider when you're delivering VARs? Inverter command yet? Of course not. Again, we have battery storage. We can use battery storage to deliver kilowatts, or we can use battery storage to deliver VARs. I've seen a lot of business cases put together that if a solar site is big enough and there is enough need on the transmission line to supply ancillary services, you may have battery storage on a site purely to do VAR support on the grid if there's a voltage deviation. And there's certainly a business case for that. So the combination of inverters and battery storage, the battery storage can be a supplement to what you're making with inverters, but of course, there's also an economic consideration on what you want to use that stored energy for. Will you use it for active power? Will you use it for VARs? Because you may not be able to use it for both. Line loss compensation is something that you have to deal with on the bigger sites that are located in more remote locations. So basically, if you've got a 100, 200, 550 megawatt site that's many miles away from the substation that it's connected to, you may not have real-time metering information from that substation that you can do control with. So if you're trying to maintain a power factor at that substation, what you're putting out of the site might not be in agreement with what is getting to the end of the feeder line between the site and the substation. So you may need to do some calculations on what the voltage drop is through that line to make sure that you're in compliance with what the interconnection itself is, and not just what's at the point of common coupling leaving the site. So lastly, with static VAR sources, if you've got cap banks or inductor banks, how are you going to use them? How many steps of capacitor banks do you have? Is it one big giant chunk that comes in or out? Or do you have smaller switches or breakers connected to the cap bank so you can bring on partial cap bank? In my first solar site, we had two 12 MVAR cap banks and two 18 MVAR cap banks for a total of 60 MVARs. And we had to pay attention to duty cycling. So when you needed some VARs, your first instinct is, we'll bring in a 12 MVAR cap bank, and then when we don't need it anymore, we'll shut that one off. Well, you don't want to use the same cap bank over and over again. You want to spread the duty cycle around so that you're engaging all of the cap banks in a relatively balanced fashion. And for that reason, you might not want to have different sizes to your cap banks. You just may want to choose which ones are turned on and turned off based on the number of times they've been cycled. So again, something to think about that the control system needs to pay attention to, but probably isn't in your original discussions when you decide you want to build a solar site. So still not quite ready to issue inverter commands for what our VAR output might be. We've just got a couple more factors to consider. And that is, again, the inverter dynamic response and the shape of the PQ curve that the inverter is capable of delivering. When I started working with solar, we had a V-shaped PQ curve, so you had to be making kilowatts in order to deliver bars. And it was like a plus or minus 0.9 power factor that the inverter could deliver. But you couldn't ask for 100 kVARs if you only had 20 kilowatts of output from the inverter. The inverter wasn't capable of doing that. Today's inverters, almost all of them have either a semicircular or a rectangular PQ curve, so you can make VARs with no active power coming out of it, or even with low active power. And taking it a step further, we have the concept of night VARs that are supported by most central inverters these days. So now, if it's 10 o'clock at night, there isn't any sun shining, but you want to make VARs, you can take in active power from one phase and put it back out in another phase, and therefore create VARs from the inverters at night by consuming active power. So this is a capability that, again, lends itself well to ancillary services, and you may be able to participate in the spot market for ancillary services, or you may be able to get an agreement that ancillary services are required. But having the ability to make VARs at night or in very low light is something that didn't exist in solar power plants years ago, but it is certainly something that the control system needs to be able to control in order for you to participate in those markets. So definitely something that you should consider when designing your control system. So now we have all the information that we need about what sources of VAR we have to work with, what the capabilities of the different devices are, and how we need to deliver those VARs out of the plant. So now we're ready to send commands to each of the inverters for what their VAR output ought to be. So as I started talking about in the beginning, I think of this control system development as a decision tree. And as you can see from this slide, there are a lot of decision points that you can factor into how the control system ought to work. Most of these things are considerations that owners don't really think about when they're deciding to build or when they're designing the PV plant itself. There are only a few of these things that you need to consider early in the design process. But certainly there are applications where all of these considerations need to be taken in the design of the control system itself. The reality for controls for PV is controls can be complex. When you have to do more than the basics, figuring out how you're going to do these things is not at all straightforward. The power purchase agreement and the interconnection agreement, most of the time, that's where the hidden surprises are found. So if I'm engaging with a customer on doing a control system, I definitely want to read through with particular care around the power purchase agreement and interconnection agreement for the things that tell me that there are requirements that aren't normal for most sites. Like I mentioned, if you're talking about a very small grid, there are more likely to be those kinds of surprises. And once the site is designed and built, that's a really bad time to try and figure out how to deal with one of these things that were overlooked early in the evaluation process. So there are very few integrators that I have worked with that really know what to look for and where to look for those things. But it is one of the things that I will pay particular attention to, like I said, when I'm doing a control system design, finding out what the real requirements are and what the objectives are of the owner are super important, because you don't want to start the design of a control system and box yourself into a position where you can't add functionality later. The decision can come down to simplicity versus complexity. A simple control system will cost you a lot less, but may not give you the performance that you really want to get from your solar site. So as I started pulling together the content for this webinar, I started thinking to myself that all of these decisions start to look a little bit intimidating. Hopefully you're working with somebody that's been through this before and knows how to answer all these tough questions to get you through your solar project quickly and efficiently. But if you are working your way through the design process for a solar site and you have questions as they come up along the way, feel free to reach out to me. I'd love to chat with you about what challenges you're faced with.